All right, so and or and not. Let me try to sum up everything. This is an imperfect abstraction in the same way that streams were an imperfect abstraction. Remember we said sometimes you had to put in explicit delays, right? And we could fix that by having a normal order evaluator. This is an imperfect abstraction also. And as far as I know, they haven't really fixed it. They've worked around it. And the workaround is in Prolog, which is the logic programming language everybody uses. There's a thing called cut. It's another special form. It says, don't go down this branch. You know, if you just matched this, don't try to apply this rule recursively. And that way, if you think about the order in which things happen, you can prevent infinite loops in your queries, in your rules. OK, so that's one thing about logic programming. Another big thing is unification. Unification was a huge step forward in computing. It was a non-obvious invention. Nobody knew it could be done, let alone how to do it, until somebody did it. And it's at the heart of making logic programming work. It is the only algorithm, basically, in the query system. So in every other kind of programming that you've seen, where do algorithms come from? They come from you, the programmer, right? For every particular problem that you're trying to solve, you invent an algorithm for solving it. In a query system, you never talk about algorithms. You never say, first do this, then do this, and so on. Or, you know, what's f of g of h of 23? You don't do things like that. Instead, you just say, here are some things that are true. And the query system uses its one algorithm, unification, to find amazing results, including the ability to kind of work backwards if you think about it in functional terms. But it's not, the query system doesn't think of it as backwards because in that set of rules for append, the three slots that go after append, you know, they're all just data. It's not like one is privileged in some way. OK, so unification. 3 is the difference between eval and qeval. I'd really like you to understand this, that when you ask a question in Scheme, you get one answer, because what eval gives you as its result is the answer to the question you asked. You know, what's the square root of 49? It's 7. Thank you. But in the query system, you can get multiple answers, maybe infinitely many answers, just because of the way the algorithm works and the way rules can be recursively applied, even though they're not procedures. OK, so qeval, therefore, doesn't return an answer. It has to somehow handle the fact that there might be infinitely many answers. And the way we handle situations with infinite data sets is using streams. So here's an application of streams. You wouldn't have to do it this way. Just as when I first started talking about streams and I wanted to know if a number was prime, you could write that little loop. Let you know, I equals 2, blah, blah, blah. Try I plus 1, and keep going like that. You can do the same sort of thing for inventing a query system. But the cool functional way to do it is to use streams. And it means that as you read the program, we are doing the evaluation for all the different possibilities in parallel, kind of, even though it's not really how it happens. So at the very end, think about the read eval print loop in the query system. It can't just be print qeval of blah, 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 because qeval doesn't return anything printable. It returns a stream of frames. So what the read eval print loop has to do is keep cootering down that stream of frames, taking each element, and remember each element is a set of bindings, and then looking in that set of bindings to find the values of any variables in your query. And again, that might involve chasing down a whole bunch of bindings, because your variable might be bound to another variable, which is bound to another variable, which is bound to another variable, which is finally bound to a value. And it has to be able to work its way through that and get to where it has values for all the variables, if possible, and then print that. So the read eval print loop is a little more complicated than it is in Scheme, because that's where you turn this stream of frames into something a human being can read. Where are you likely to see the query system in the wild? That's a good question. Europe. Remember I said invented in France? Americans, for some reason, mostly aren't very interested in logic programming. There are little exceptions here and there. I'm not sure if it's still true, but I think it is. UW, University of Washington, is kind of a hotbed of logic programming. The closest thing to it that you'll see in the wild in this country is database query systems like SQL, which are very similar in spirit to this. At one time, the government of Japan had a regulation saying that all the programming for, I think then we were up to 4th generation computing, was going to be done in Prolog. It's just like in this country, the Department of Defense has a rule that if you want to program anything for them, it has to be done in Ada, which is this really terrible language. Don't tell Paul Hilfinger I said so. He likes Ada. It's just so big and... But anyway, in Japan it was Prolog, and they've backed off from that. But you see a lot of still Prolog code in the wild there. Best I can do. Other questions? It's not. All right. On Friday. Oh, yes. Go ahead. Is it massively inefficient? No, because of the reordering and the memoization of streams. So it's much more efficient than it looks. Yeah, no, it's not bad.